Okay, let's wait 1 minute for more people to come. Okay, let's start. So today my topic is Apache Arrow, a unified language across big data. About me, I'm Yibo Cai from ARM CE OSS Essential Engineering open source software team. I'm focusing on big data and storage open source software development. And I am Apache Arrow commit. First agenda. First, I will give an overview of Apache Arrow project, what Arrow does, what's the problem Arrow tries to solve. And then I will introduce the Arrow C++ library. So all the components of the Arrow C++ library. And then I will introduce the Arrow columnar format with some samples. So Arrow columnar format is the core of Apache Arrow. After that, I will also introduce the computer kernels. So computer kernel is do some computations based on the Arrow columnar format. And also FlightRPC. FlightRPC is to transmit Arrow data from one machine to another. So this makes Arrow not only run in standalone in one single node, it can also use the distributed computation environment. Then I will introduce the Parquet. Parquet is also a columnar format, but it's for on-disk storage. So Arrow columnar format is for in-memory computations. And finally, I will give our contributions overview of what we did and how we improved Arrow communities on ARM platforms. The overview. So Arrow is an open standard for efficient columnar data exchange. So you can see from the left picture is the situations before Arrow. So you can see there are many open source big data or data science projects. So these four dark blue boxes are database or storage, on-disk storage projects. They have their own file or storage formats. And then above for light blue boxes are in-memory computation projects, Spark, Pandas. So they also have their own in-memory data representations. So for all these projects to interoperate with each other, they have to so all the data have to be serialized and deserialized to transfer from one project to another. So this is a big waste of resources, both CPU and the memory and the network bandwidth. So this is a situations where Apache Arrow tries to resolve. So after Apache Arrow, so all these projects, storage or in memory, they all converted to the Arrow columnar format in the memory to do computations. So there is no extra effort to do data serialization, deserializations, or other kind of data manipulations across these projects. So it will make the unified all the big data projects to use one single language. So this is the what Apache Arrow did, helps the community. So about the Apache Arrow community, so Apache Arrow is in Apache Software Foundations, and it's already widely adopted in big data and the data science community. So this is a very mature project. It supports, you can see the picture, at hardware level, it supports x86, ARM, and PPC. So we are the maintainer of the ARM features. So at the operating system level, most prevailing Linux distros are supported, and also supports Mac OS, including M1 and Windows. So above this distro is the API levels. So the Arrow implementations. Arrow implementations supports 12 languages. So most common used language are all supported: C++, Python, Java, Rust, and Go, and many others. So they are also so in the application levels, there are many famous projects also powered by Arrow, like Spark or Pandas MetaLabs, or have Arrow built in to improve, to enhance their performance in data transfer or data manipulations. So this is the Arrow C++ library. So I just said Arrow supports 12 languages, but the Arrow C++ library is the most active components that is developed in Arrow community. So the C++ library contains many sub-components. So in the middle, this yellow box is the Arrow Columnar Format. So this is the core of the Arrow project. So it includes a bunch of data structures and utilities to manipulate the data structures. And above this is the Arrow computer kernel and FlightRPC. So Arrow computer kernel is to do the computations based on the columnar format. And FlightRPC is to transfer the data across network to other nodes, also running Arrow projects. And under the columnar format, this blue box is the Arrow dataset. So Arrow dataset is to adapt file formats, the various file formats into the Arrow projects, like CSV or JSON or Parquet. All these are very common data science files. So the dataset module is to convert these file formats into the Arrow columnar format. So the upper level computer kernels of FlightRPC can do computations or transmissions on this data. At the top is a query engine. This is a very new feature. And at the lowest level is the Arrow file system. This is the abstraction to convert local or remote files to a stream API and to bring it, to give the stream to the Arrow dataset. So these two components we didn't touch very deep, so I did not introduce them in these slides. So what I will introduce deep is the computer kernels, FlightRPC, and the Arrow dataset, 3 core component modules. First, I will introduce the row and versus columnar format. So traditionally, this is an example of the data set. So there are 3 columns in 3 colors, and there are 4 rows. In traditional row-based storage buffers, you can see each row is stored continuously in memory. So the columns are discontinuous. So you can see the colors are not continuous. But in the columnar format, you can see the same color are stored together. So it means the same colors are stored continuously in memory. So this format is columnar format is suitable for analysis tasks or EP process, like analysis to so for example, I want to aggregate the source IP column. I want to find which IP occurs most frequently. So basically, I will need to scan all the source IP and then use a map to map the source IP to the count. To do this, if we use a row-based buffer, we have to read in all of the rows one by one. But the session ID and the timestamp, so these two columns are not used at all, but they have to be read in and then discarded. So this is a big waste of memory and both I/O and also for memory and for CPU cycles. But for columnar buffers, we can read only the source IP in, so there's no extra overhead, and the source IP are packed together, so it's also easy to enable vectorizations, optimizations. So this is a big win. So columnar format is very suitable for OLAP, for analysis workloads. Now the Arrow columnar format. So Arrow columnar format is designed for fast in-memory computations. So this also eliminates the necessary for serialization and deserializations. So first, I will introduce the fixed size list. So for fixed size means that each field, each slot is storing same size values like this integers with 62 bits. So this is a 1D array example that has 4 elements. The second element is missing. So missing data is a very common in data science. So internally, Arrow will represent this 1D array with 2 buffers. First, the value buffer is green one. Value buffer, it has 4 values mapping directly to the original values. You can see the second value where data is missing. It can be any padding values. Any value is okay. Just the same size as the other values. There's also a validity bitmap to indicate that which value slot is valid. So if this value slot contains a valid value, the validity bitmap will be 1. And if it's not a valid value, data is missing, the validity bitmap will be 0. So we can see this is 0 to indicate the second value is missing. So this is straightforward. Now for variable size. So variable size is a bit more complicated. See there, for this example, we have 4 elements. First element is a subarray with 3 integers. Second element is missing. The third element is also integer array, but with 4 elements. And the third element, fourth element is an empty array. So first, the validity bitmap. So this is simple. We have 4 elements. Second element is missing, so 1, 0, 1, 1. So this is simple. The value buffer is a bit interesting. You can see the value in the value buffer. The first subarray 2 minus 7, 5 is stored here. But the next 4 values are actually from the third subarray. You can see this. They are stored continuously. So even though there is a gap, so there is a data missing in the second element, but this is the value buffer only contains valid values. No, the missing data is not padded here. But with this value buffer, how can we get a slice out the required subarrays? So this is the offset buffer does. In offset buffer, we store the pointer in the value buffer to indicate the starting and ending point of starting and ending position of subarrays. So for example, this is first is 0, second is 3. So we use 0 and 3 as the index. We can slice out these first 4 integers. So first 3 integers, 2, -7, and 5. So this is the first subarray. And with say 3 and 7 can slice out these 4 elements, 4 integers. For the missing data and the empty array, you can see the according offset are 3 and 3. So so that means the starting and ending point are pointed to the same position. So it also means the size is 0. Also for 7 and 7, the last empty array size is 0. Okay. So this is for struct. For struct, this is a table. Struct is similar to a table. You have 2 columns in this example. We have names, Jew, Mark, and some missing data. So also we have age, fixed size, integers. So there's also some missing data. So the name buffer is the variable size array. It has Jew, Mark stored, the characters stored continuously, and they use offset, like the last page. Introduced the offset to slice the according subarrays. And then for the age, there's a fixed size, so it's easy and just fill the values and the missing values are filled with any padding values, and use a validity bin to point to that to indicate that the last 2 values are missing. So the point for Arrow Columnar Format is that it makes the data representation is suitable for in-memory, faster in-memory computations, but also eliminates the necessary to serialize, deserialize data. So the data format is memory address, starting address independent. So you can copy the data block to one memory address to another memory address, but the semantics is not changed. You did not need to any extra effort to maintain the data buffers. So now the computer kernels. So we have defined fancy columnar format. How can we do interesting things about this? So the computer kernels are for this purpose. For computer kernels, it performs computations directly on Arrow columnar data. So Arrow have 3 kinds of computer kernels, like a vector and scalar kernels, also aggregate kernels. So for vector kernels, like sorting, the output is dependent on the relationships of each element. For scalar kernels, this is element-wise computations, like we adding 2 sub-arrays and resulting to a new array. So each element by element. For aggregate kernels, we reduce a vector into a scalar, such as we calculate the minimum of an array, or we calculate the variance of an array. So input is a vector, but output is a single scalar. Okay, now for FlightRPC. FlightRPC is to transmit the arrow buffers over the wire. So transport layers. Currently, they support gRPC. So it makes the arrow suitable for building distributed computation platforms, not only running on single host. So FlightRPC has much higher performance than ODBC and JDBC. So this picture is a basic architecture of the FlightRPC. So this is a simple client-server architecture built upon the gRPC. So it defines some upper-level protocols. So this is no miracles here. It is just a simple client-server execution flow. But you can see from the right is interesting. It compares the execution time of data intensive query across network through ODBC and through Aeroflight. You can see the lower is better, so the time is much more slower for the Aeroflight to execute the same queries. So basically, this means Aeroflight has much higher performance than the traditional ODBC. The reason is that the serialization, data serialization, deserialization is not necessary for Aeroflight. So this is a very expensive cost for data intensive applications. So this is where Arrow Columnar Format helps. So it reduced the serialization overhead and improved the performance significantly. Okay, now the Parquet. Parquet is a columnar format for on-disk storage. So Arrow is a columnar format for in-memory computations. For in-memory computations, all the data are, but Arrow format is not suitable for on-disk storage because the disk storage we need a space I/O efficient formats. But Arrow in-memory format is not suitable for this. So Parquet data is a space I/O efficient. It is the data is encoded and compressed, and also Parquet is also a very widely used project, already used extensively in big data communities. So Arrow has the Parquet C++ implementation is now a sub-project of Arrow, and Arrow has very great support to Parquet data sets. And we did many works on Parquet optimizations, especially the encoding and decoding methods. So encoding decoding can benefit from SMD, from neons. So the last time we introduced our contributions to Arrow, to Apache Arrow. We submitted about 100 patches in 1.5 years, and most patches are for performance optimizations on ARM. Some optimization also for general architecture feature improvements. And we also did many feature developments for computer kernels. We are the major contributor of aggregate kernels. And we also refined many core component framework modules. And we have many patches for performance improvement, like the sorting kernels and the summations and the byte splittings. And many patches have tens or even hundreds of performance improvements. For FlightRPC, the most important contribution we did is to optimize the multi-core scalability. So the FlightRPC was not scalable. So you give it more threads and more cores, but the performance doesn't improve, the throughput doesn't improve. So after our optimizations, the performance, the throughput becomes almost linear scalable to the number of cores. So this is the most important patches we committed to the FlightRPC. And we also added many other features like unique socket RPC support for local RPC, and also optimize the compressions and compression benchmarks and the latency estimations and many other features and optimizations. And for Parquet, we did neon optimizations of encoding and decoding modules, and with about 10x performance improvements. And we also have many SRMD optimizations ongoing. Okay, thank you. That's all.